Okay, recording is started. All right, hi guys. So many of you would have noticed that we stopped at this point here in the last video. And somehow in the in-person lectures, we missed a few slides. I don't think we actually missed them because I remember going over them, but somehow this is not in the videos. So anyway, the most important thing now is to get this video up and running so that you guys have a source of information to look for these few slides that were missed. And luckily, these sections are not too difficult. And maybe a little bit interesting because I think this is new stuff. This is one of the sections that you might not have seen in high school, which is a good thing because I know some people get really bored doing the same thing over and over again. So let's try and look at something a little bit interesting here. So what we are looking at here is the main section is equations, inequalities, and absolute value. So we've covered a few of these already, and now we're going to look at absolute value equations. Okay, so some of you guys may have seen something that looks like this right here. Absolute value of x. You might have seen this in metric, I guess maybe when plotting graphs at some point. Some of you may remember this. Let me just draw this here, this familiar form of graph of absolute value of x, which kind of looks like a V, where the tip of the V is at the origin of the xy plane. Right? You may have seen that. So if you have, that's good, but this is not what we're looking at here. We're not looking at a picture, we're looking at finding the values of x which go into the absolute value to make this equation true. And when I say make the equation true, I mean make the left-hand side equal to the right-hand side. That's what a true equation means. Okay, so before we look at an actual example, let's try to think about intuition behind this before we look at a method which always works. So the intuition behind this equation here, say this one right here, I'm pointing with my pen, I hope you guys can see it. Absolute value x is equal to 5 is asking the question, what values of x go into this equation make this equation true? All right, so intuitively we can see, we know that an absolute value, just as a recap, is something which always gives you the positive version of a number as output. So for example, the absolute value of -2 is just 2, and the absolute value of 2 is also 2. All right, so keeping that in mind, the only two values that make this equation on the left-hand side true would be x is equal to 5 or x is equal to -5. Right? Because either of these values plugged into the equation will make the left-hand side equal to the right-hand side. So this is clear just by looking at it. But now if you want a method that works for any equation, see, this is a trivial one, but if you want something that works for any equation, what we do is see, it's written here on the right, we look at the positive and negative version of the equation. So for this one right here, we will write it first as the positive version, which is just x equal to 5, and the negative version is just negative x equal to 5. So the positive and negative happen only where the absolute value is. So we take the positive version of the absolute value, that's this part right here, and the negative version of it, that's this part right here. Note the sign of the 5 doesn't change. It's just the absolute value part, which is only the x. So the 5 itself doesn't change. Now, these are just two equations that we can solve to get our values of x, and you'll agree that the one on the left is already solved. There's not much more we can do with this, but the one on the right, we can perform one more step, move the negative sign to the other side, and get x is equal to -5. So again, we've come with the same solutions that we derived intuitively at the top, but this time we're just using a method. So now using this method, we can solve any absolute value problem. Since I'm recording this at home, I don't need to wait for you guys to do examples. I'm just going to be doing them. And you can pause the video if you need to and try these. I'm going to go ahead and do this one up here. X plus 5 absolute value is equal to 15. Okay, so pause and give it a try if you need to. I'm just going to go ahead and write this as the positive version, which is x plus 5 is equal to 15. And the negative version is just negative x plus 5 equal to 15. Okay, now take note of the bracket. This bracket is important because we are keeping in brackets the absolute value part and the negative sign comes on the outside of that. Now this is important because the negative sign is going to distribute throughout. If we didn't put the bracket, then it would be a completely different thing. So just be aware of that. Okay, let me solve the one on the left first because that looks a lot easier. I'll rewrite this as x is equal to 15 minus 5, or x is just equal to 10. Right, that one looks fine, straightforward. And the one on the right, again, it's not really difficult. You just need to be aware of the negative sign on the outside. Distribute it, it becomes negative x minus 5 is equal to 15. I can move the minus 5 to the other side and make it a positive 5. So we end up with x is equal to, negative x is equal to 20. And last step, x is equal to negative 20. Right, for this, you can either multiply by negative 1 or divide by negative 1. Whatever is your preference, it doesn't matter. Just get to the final step and be logical in the way you get there. Okay, so these are two solutions. If you want to check these, you can just plug these numbers into the original equation and check if left-hand side equals to right-hand side. You'll find that both these values make that true. Okay, so here's another example at the bottom. I'm just going to go ahead and do this one as well. Again, same principle. We take the positive version and the negative version. 2p minus 26, that is the positive version, or negative 2p minus 4, all in brackets, is equal to 26 version. I'll do that first because that's more straightforward. 2p is equal to 26 plus 4 on the side. Is that right? Yeah, that's fine. And then we simplify that to 2p is equal to 30. Sorry. Yeah, that's fine. And then we divide by 2 on both sides, which is just 15. You guys know what I did there? Okay, and the right will distribute it. So let us do that. And we get negative 4 is equal to 26. Again, being careful with distributing that negative. So negative 2p is equal to 26 minus 4, which is just 22. I'll write that in one go. Now we can divide everything by negative 2. And we end up with p is equal to negative 11 on this side. Okay. I think we've done enough to get the hang of this. So for this last one, I'm just going to show you guys how to deal with something where the left-hand side doesn't have just an absolute value. It has a few things going on here. So the first thing we need to do is to isolate the absolute value part on the left-hand side. Again, you don't have to do this. It's not absolutely necessary, but I find it to be the best way to get everything in a form where it's easier to not make a mistake, right? So I recommend doing this, even though you don't absolutely have to. So I recommend what we do is we move the negative 5 to the other side. So what I'm left with here is 3, 4w minus 1 absolute value is equal to 10 plus 5, which is 15. Then divide both sides by 3. We end up with 4w minus 1 is equal to 15 over 3, which is just 5. And now we get to a place where this equation resembles what we've seen before. So we know what to do here, right? Some common mistakes to be aware of. Sometimes people will take this 3 and distribute it into the absolute value sign. Things get a bit messy when you do that. And the absolute value, remember, is not the same as a bracket. So we avoid doing things like that. It's always best to just keep the absolute value alone and deal with it by itself. If I'm not mistaken, I think there are ways to multiply this inside, but there's certain nuances that happen here which can cause problems. So it's best to just avoid these things and just do it like this. It's just always safer, always neater. Also, it makes my life easier when I'm marking, right? Because it's easy to assign marks to every step in this way. Okay. So from here, you guys know what to do. I don't need to do the rest of this. Give it a try. Okay, now we're going to solving inequalities containing absolute values. So this is just one step further. It's still the same idea though. just that here now we have to start plotting these graphs, or plotting these solutions rather, on a number line. Okay, again, some of you would have seen this before. So let's just go over this one quickly as well. The absolute value of x is less than or equal to 4. So here we do the same trick we used before. We take the negative and positive solution. I'll start with the positive one and write this as x less than or equal to 4, and the negative one becomes negative x less than or equal to 4. Now remember, with inequalities, when you multiply or divide by a negative, you have to flip the sign of the inequality. So solving this inequality on the right, we will just, let's just say we multiply both sides by -1, then we end up with x greater than or equal to -4. So these are the two solutions right here. Again, the one on the left-hand side, we didn't have to do anything. The first step was basically the solution already. Okay, now this is an important step. I'm going to change the color of the pen. For this, we plot the solution. So we draw a number line. 0, 1, 2, 3, 4, 5, -1, 2, 3, 4, and 5. And let's change the color again. Okay, so now we find our endpoints. And we see here the one on the left is 4. So we come to 4 and we draw a circle. Somehow I've not selected the pen. Let's do that again. Come to 4 and draw a circle. And now because the inequality is less than or equal to 4, because it's less than or equal to, we color the circle in to make a solid dot. If it was just less than, we would draw an open circle like this and just leave it like that. Okay, but that's not the case here, so we color it in. And now we draw an arrow going in the direction of our solution. We can see the inequality points left, so our arrow must point left. I'll draw an arrowhead here for now, but okay, that's fine for now. And on the right, our solution starts at -4, according to this inequality. So at -4, we draw a circle, we color it in, and now the solution goes toward the right from here. Okay, and what happens is we see these inequalities meet at some point. So I can erase the arrowhead and just let them meet. Let's just allow them to meet. Just like that, and try and draw this neater than me if you can. Okay. So now another important point is that it's not necessarily true that these solution sets will always meet in the middle. Sometimes they may be pointing in opposite directions. But importantly, when they meet, it means we can write our final solution in one compressed form. That is the lower endpoint less than equal to, well, the less than equal to or less than depends on what we have in our actual solutions, right? So we're taking it straight from here. Let me put the arrow so we can see. I'm taking it straight from here. Right, so anyway, the compressed form, -4 less than equal to x less than equal to 4. That's our final form. But we can only use this final form if our solution meets in the middle in this number line graph that we've just drawn. Okay, so here's a neater version of the solution down here. And we're given another example here, I guess, to show a case when the solution sets don't meet. Okay, so absolute value x greater than 3. So let's look at this one. I'm going to do this quickly because I hope we get the point by now. This is going to be x greater than 3, and the negative version will be negative x greater than 3 or x greater than -3. Sorry, we must flip that inequality. Isn't that right? Yes. So just be careful for that mistake, because even me, I look at that quite often and make the same mistake. Flip the sign of the inequality when you multiply or divide by negative. Easy mistake to make, right? We don't want to lose marks for nothing. So just be careful of that. Right, so once we have this, we plot our number line very quickly. 0, 1, 2, 3, 4, -1, -2, -3, -4. Go to our other color pen. And now at -3, we draw an open circle this time. We don't color it in because the inequality says less than, not less than equal to. And the arrow from the -3 solution points to the left. So we take this and point it to the left. And at 3, we have a solution that points to the right. So we do that as well. And now see these solutions don't meet one another. So we can't compress our solution further. So we leave it exactly as it is, and for that we get full marks. We don't have to do anything further. Okay, and why is this shown again? Okay, so this slide shows us the same solution we just reached in a neater form. And this is a bit of a general rule here, showing when you can compress your solution and when you can't. So exactly what we just discussed. Okay, but have a look at this for a nice summary. If you guys need to recap what we just went over. Okay, and now another example. Okay. So let me at least set this one up for you guys. I'm not going to do this whole thing. Let's just see. Yeah, okay. So this one, again, same principle. When you have an absolute value on one side with other stuff, try to get rid of all that other stuff, move it to the right-hand side and isolate the absolute value on the left. So here we will be left with 2y plus 6. There's a 3 in front, less than 27 plus 9. Okay, which I'm going to write as 36 in one go. Okay, then we can divide both sides by 3 to get 2y plus 6, right? Less than, and that should give us 12. Okay, so once we get here, I'm presuming everyone knows what to do. I'm just thinking whether I should do this example. Let's look at the one above. Is it close enough? Actually, no, let me do this one. Let me not assume things. Let's just get it done so it's on the video. Okay, so here again, we take the positive and negative version. So the positive version is 2y plus 6 less than 12. The negative version is negative 2y plus 6 less than 12. Again, see exactly the same as with absolute value equations. Same idea. Now the one on the left, we write this as 2y less than 12 minus 6, which is just 6, or y less than 3. That's one solution. The one on the left becomes negative 2y negative 6 less than 12, or negative 2y less than 18, positive 18. But now we divide throughout by negative 2. So we change the sign of the inequality, and we get a 9 here. Or negative 9, sorry, because we're dividing by a negative. Okay. Right, now let's draw the graph for this one. It's going to be a bit of a big graph because we've got negative 9 and positive 3. But we can make it fit here. Yeah. Okay, let's just do that. Okay, so I'm going to skew this graph, but let me put the 0 somewhere here, because here we just need 1, 2, 3, 4, and this side we need to go to 9. Actually, no, sorry, the negative needs to go to 9, so we need to skew this more the other way. Let's put the 0 somewhere here. 2, 3, 4, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. Okay, we just about made it. So now, same idea. We go to negative 9, draw an open circle, go to 3, draw an open circle, and we can see if we follow the directions of these inequalities, the solution will meet in the middle. So we just cover this line. Okay, so again, we can then compress this to negative 9 less than x less than 3. Okay, and now we have to be very aware of cases when there are no solutions to these inequalities. And I'm always wary of this because with equations, when you have no solution, if you solve those equations, you get strange things happening, right? You guys may remember the previous section where we get 0 is equal to 0 or some constant is equal to another constant if you have infinitely many solutions. If you have no solution, you will end up with a contradiction at the end, something like 0 is equal to 1 or something equal to something which is not true. So you end up with an untrue statement for equations. Unfortunately, with inequalities, if you try to solve something which can't be solved, you will still be able to solve it. You will get an answer. So here we have to be careful because we have to be able to tell ahead of time before you solve this whether or not it is solvable. And for that, we need to develop a method because it's not immediately obvious. Like look at this example down here. We know there's no solution to this, but it's not obvious when you just look at it. So the first thing we do, always the first thing we do is we isolate the absolute value to one side, and maybe from there it will become obvious. So I'm moving this 9 to the other side to get -2. Okay, now when you guys reach a stage like this, you need to be able to tell whether or not this is solvable. And I'll tell you guys now it's not solvable. The reason being, we have the absolute value of something. It doesn't matter what that something is. It's the absolute value of something less than equal to -2. Now think about what an absolute value is. It means it doesn't matter what x is that goes into this equation. That x that goes into the, sorry, not equation, inequality. So I'm saying the x that goes into this inequality could be anything. It could be positive, it could be negative, it doesn't matter. But the output of the absolute value will always be positive. What goes in doesn't matter, but what comes out is always positive. So if what comes out is always positive, could it possibly be less than equal to -2? It can't be, right? It can't be negative. It's always positive. So if you have an absolute value claiming to be negative, like this one here, then there's no solution. So we must remember this point. If, let me just write this here. If an absolute value claims to be negative, then there is no solution. Yeah, I usually pause for questions at this point, but if you guys have questions, you can ask me in class during the breaks or before we start or at the end of the lesson. You know, we always have a fair amount of time in between, so please don't hesitate to ask. These are new concepts, so if anyone's confused, just let me know. Okay, I think we have a few more slides to go and then we're done. Rational expressions, okay. All right. So now we look at rational expressions. The main point of this entire section, I'm just going to jump straight to it, is finding domains of expressions. So you guys may have heard about domain and range in high school. Later here we'll deal with something called a codomain. I'm not going to get into detail about that now because we will hear about that later. Important thing for now is domain. So if I'm given an expression like this, 3x plus 2 all divided by x minus 4, and I'm asked to find the domain of this expression, it's just asking me to find the allowed x values. All right, so what's on the top of this doesn't matter. The numerator is not important. Only the denominator matters, and that's x minus 4. So this whole section is based on the fact that the denominator cannot be 0. That's the entire thing here. So it's a very simple section. The denominator cannot be 0. So to find the domain of this expression, we just find the value which makes the denominator 0, and we exclude that. So here we can clearly see x cannot be 4, because then we get 4 minus 4 is equal to 0. So we know that x cannot be 4, but x can be anything else. So the domain of this is simply x an element of real numbers, comma, x not equal to 4. That's the answer. It's as simple as that. Right? There's nothing too complicated about this section. And if you want to write this more formally, you can write it as x minus 4 is equal to 0, and solve this for x to find the value which makes the equation true. and that value is 4. All right, so whatever value you find, just exclude it. And we say x is an element of real numbers, comma, x not equal to the value we just found, which is 4. That's the more formal way to do it. Set the denominator equal to 0, solve x, and then exclude that x value from all real numbers. Yes, okay. So the second example is just making the point more strongly that what's on the top or what's in the numerator does not matter. Right, in this example here, all we see at the bottom is x plus 7. So all we need to worry about is x plus 7 equal to 0. What value makes this true? It's just x is equal to negative 7. So the x is an element of real numbers, is our domain, but we must exclude x is equal to negative 7. Okay. So again, that's the answer. Of course, when we have trinomials at the top, we have to be aware that sometimes these things can factor out and make things simple or more difficult, depending on how they ask us the question. But in this case here, again, the placement of the section is quite terrible because factorization is the section that comes after this. Okay, so maybe I'm not going to worry about the factorization questions for now because we don't deal with that section just yet. So just worry about the denominators. The numerators we can just completely ignore for now. Okay, but there's a point I want to make about numerators, which I will make here. Sometimes we were asked, again, I don't fully agree with this, but the notes that we are given explains things in this way. So we have to just be aware of this. And this is what I mean right here. Look at this expression, 5x squared over 25x. 5x squared over 25x. You guys will agree with me that this is exactly equivalent to 5x over 25, right? Simplified. Now these two expressions are separated by an equals to sign, meaning they are exactly equivalent. There's no difference between these two things. They are in fact the same thing. However, if you look on the left, you will see that here the domain is x, an element of real numbers, comma x not equal to 0. Right? X cannot be 0 here. If it is, the denominator goes to 0. And on the right, the domain is just x element of real numbers. There's nothing to restrict it. Now, the thing that troubles me here is these are two completely equivalent expressions, however, their domains are different. And this, to me, doesn't make sense. So to me, I actually don't like the fact that we write the domain of an unsimplified expression on the left. Because to me, you have to simplify it before you can find the domain. Things that cancel out must cancel out, because even if you check this with some kind of plotting tool online or Mathematica or something, if you plot these two things as functions, and if you check what the domain is, they will both be identical. However, the notes tells us that that's not the case. So just because that's the case in the notes, when I mark, I will mark both correct. Even though I'm telling you guys what actually is the correct thing to do, if you follow the notes, that's okay. I just want you guys to be aware of what the correct thing is here. Okay. So just be aware, if you see this in a test or an exam or anything, and it says find the domain of the original expression, they mean find the domain of the expression before simplifying and canceling terms on the top and bottom. Again, even though to me this is a bit of nonsense, that's what they ask us to do. So again, unfortunately, just follow the way they ask us to do it. But if you do it the correct way, I will mark it right. Okay. And here's another example for you guys to try. Maybe after we learn how to factor, you can try this example. So I'm going to skip that one for now. Solving rational equations. Okay, this is the last thing we need to look at here. Okay, so I'm just going to go ahead and solve these two equations. So this one at the top, the best way I can see to solve this would be to multiply the right-hand side by 2 over 2. Remember, 2 over 2 is the same as 1, so it's as if we did nothing, so it's mathematically legal. And in doing that, I will get a denominator of 8, which is the same as the denominator on the left. So that gets me a common denominator. Okay, so I rewrite this as x plus 5 over 8 is equal to, let me write on the top that I'm multiplying the top and the bottom by 2. So I get 14 on the top and 8 at the bottom. Okay, I'm not sure why the pen did that, but let's sort that out. And now I can multiply both sides by 8 to get rid of the common denominator. We get x plus 5 is equal to 14, or x is equal to 14 minus 5, which is just 9. Now let's look at this other one at the bottom. Okay, they seem a bit out of place here, but anyway. Okay, so this one here, again, let's just try to isolate x, get it alone on one side. X over 3 is equal to 4 over 3 minus 1. And now we can rewrite 1 as 3 over 3, right? So I'll write this as 4 over 3 minus 3 over 3. At the top here, we have 4 minus 3, which is just 1. So 1/3. X over 3 is equal to 1/3. I can now multiply both sides by 3 to get rid of the 3's at the bottom and just have x is equal to 1. Okay, that is the solution. And from there, we've now reached the place where we have reached in the lessons in person. So I can stop the lecture here. I think the only example I haven't done in person is this one here with this application problem. But again, this one here, I'd ask you guys to please look at the module manual because the detailed solution is there. And if that doesn't make sense to anyone, then you can ask me. Yeah, because this is a very far out there, unlikely, strange problem to see, but it's nice to look at it anyway, just to get a bit of an idea of how to think about these things. Okay, again, if anyone has trouble with it, please ask me. Okay, guys, then I'll end the video here. Happy studies, and I will see you next time when I see you.